Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss potential and electric field of a dipole. Let's begin. First, we derive the potential of a dipole, and by applying the relation between potential and electric field, we can easily find out the value of electric field of a dipole. So, consider an electric dipole. First, that is calculation of potential. Calculation of potential. When the dipole located at origin, dipole located at origin, let me consider an electric dipole that consisting of charge minus q and plus q and separated by a distance 2l, and here we choose the origin at the midpoint of electric dipole. This is the dipole. Charge minus q plus q, its distance be 2l. So, in that of negative section, that is minus l, positive section, that is plus l. These are at the points A and B. The points are A and B. At point A, negative charge, at point B, positive charge of the dipole. Let P be the point. Here we take the point P having the position vector r vector from the origin. Here the position vector of P, that is r vector from origin, and that creates an angle theta with the positive direction of x axis. The angle is theta. OP is the r vector. OA minus L vector, OB plus L vector. Let we join the line AB and BP. Look here, that is the direction, that is the direction. So, in triangle OAP, we can use triangle of vector addition. Therefore, AP is equal to r vector plus L vector. That result will be r vector plus L vector AP. triangle of vector addition, two sides are in the same direction, then the resultant will be in the opposite direction. Same direction, the resultant will be in the opposite direction, r plus l. Again, in triangle OBP, OB the plus l vector, OP is the r vector. So, the resultant BP, this is the OB. So, the resultant BP is equal to r vector minus l vector. Okay. Now, we have the resultant as AP is equal to r vector plus l vector, BP is equal to r vector minus l vector. Then we can find out the potential at point P due to these point charges. So, potential at point P due to minus q charge, how much? Right here, potential at point P due to minus q charge. That is V1, which is equal to 1 by 4 pi epsilon naught charge that is minus q divided by its distance, magnitude of distance, that is r vector plus l vector, that is r vector plus l vector magnitude. Okay. Then potential at point P due to plus q charge, and potential at point P due to plus q charge. Let V2 is equal to 1 by 4 pi epsilon naught plus q divided by its distance r minus l magnitude. Now, the total potential at point P due to both the charges means due to that dipole. Here, therefore, total potential at point P due to both the charges is V is equal to V1 plus V2, or V is equal to V1 plus V2. Here we have to take q by 4 pi epsilon naught as common. Inside that bracket, 1 divided by r vector minus l vector magnitude minus one divided by r vector plus l vector magnitude. Okay. Let equation number 1. Look at here, the angle between L vector and R vector, let theta. So, R minus L can be written as, we write r vector minus L vector magnitude, that is the dot product of r vector minus L vector dot r vector minus L vector its square root, that gives rise to the magnitude of r minus L. Now inside that bracket we have r dot r plus L dot L minus 2 r dot L to the power half, that is r square plus L square minus 2 RL, the angle between these two, cos theta to the power half. But we have to calculate 1 divided by r minus L. So, the reciprocal of that quantity 1 divided by r vector minus L vector magnitude, that is to the power minus half, r square plus L square minus 2 RL cos theta to the power minus half, as we take the reciprocal. Here we take r square as common. If we take r square as common inside that of bracket, then r square to the power minus half, r square to the power minus half, that is r to the power minus 1, that is 1 by r. So, 1 by r to that of outside. So, inside that of bracket term will be 1 plus L square by r square minus 2 L divided by r cos theta to the power minus half. Here not confused, inside that of bracket I take r square as common. Since I take r square as common, that bracket term will be this much, and r square to the power minus half, that means r to the power minus 1, that gives rise to 1 by r. 1 divided by r vector minus L vector magnitude. Look here, if the observation point means the point P, the position vector r is much greater than as comparison to the distance of the dipole. Here we take, since r is much greater than L, that is L square by r square is much less than 1, and it is neglected. These values will be neglected. So, that bracket term will be 1 by r minus L magnitude is equal to 1 by r 1 minus 2L divided by r cos theta to the power minus half. Using the binomial theorem to expand 1 minus 2L divided by r cos theta to the power minus half. Here using binomial theorem, we have 1 divided by r vector minus L vector magnitude is equal to 1 by r 1 plus L by R cos theta. All other terms are neglected. Neglecting terms containing L square by R square. These are the higher terms. Or we have 1 divided by R minus L magnitude is equal to 1 by R plus L by R square cos theta. Similarly, for 1 divided by R plus L can be derived. Similarly 1 divided by R vector plus L vector magnitude will be 1 by R minus L by R square cos theta. Here we have 1 divided by R minus L, here we have 1 divided by R plus L. Now putting these values in equation number 1, we have here we write putting these values in equation 1, we get, here we put the value, we have the potential V is equal to Q by 4 pi epsilon naught. In place of 1 divided by R minus L, we get that value, and in place of 1 divided by R plus L, we put that value. So here we have 1 by R plus L by R square cos theta minus 1 by R plus L by R square cos theta. 1 by R minus 1 by R cancelled out, that is Q divided by 4 pi epsilon naught 2 L cos theta divided by R square, Q into 2L. We write here 2QL cos theta divided by 4 pi epsilon naught R square. Here the dipole moment P is equal to charge into length of the dipole, that is 2QL, that is P cos theta divided by 4 pi epsilon naught R square. P cos theta, that can be written as P vector dot r cap. R cap is the unit vector of R cap is the unit vector of R vector. So P cos theta is equal to P vector dot r cap divided by 4 pi epsilon naught R square. Again R vector is equal to R vector magnitude and its direction, its unit vector. So in place of R cap we can write that is R vector divided by R. In place of R cap we write R vector divided by R. So we have P dot R vector divided by R. So that result will be RQ 4 pi epsilon naught RQ. This is the expression for potential. P dot R divided by 4 pi epsilon naught RQ. Now that can be written in terms of gradient. Here we know grad of 1 by R is equal to R vector divided by RQ. R vector divided by RQ can be substituted as grad of 1 by R. So that expression will be further written as V is equal to okay. Here grad of 1 by R, that is minus R divided by RQ. So minus 1 by 4 pi epsilon naught P vector dot grad of 1 by R, potential in terms of gradient. Now we get the expression of potential at point P when that dipole is located at the origin. It has the special cases when P, the point P lies on axial line of electric dipole on positive side. Positive side in the sense that P lies the axial lines, means here positive direction. Then what should be the expression? That is the angle theta will be 0 degree. Then the expression potential, that is 1 by 4 pi epsilon naught P divided by R square. Again, when the point P lies on axial line of electric dipole on negative side. Negative side means that point P lies here, that is the axial line. This portion is the positive section, this portion is the negative section. If that point lies in the negative direction, so theta will be 180 degree, that is theta will be 180 degree. Then the expression for potential minus 1 by 4 pi epsilon naught P divided by R square. Another condition, when that point P lies on the equatorial line, when P lies on equatorial line. Look at here, what is equatorial line? This line is the equatorial line. If P lies on that of equatorial line, then the potential will be, here the angle theta is 90 degree, that is theta is 90 degree. When that is axial positive direction, theta is 0 degree. When axial negative direction, theta is 180 degree. But when that P point lies in that of equatorial line, theta will be 90 degree. So theta 90 degree, then the potential will be 0, then potential V will be 0. So there will be no potential when that point lie on that of equatorial line of that of dipole. These are the expressions when that dipole located at the origin, but when that dipole located at arbitrarily, when that dipole located at arbitrarily, then what should be the expression for potential? Look at the figure, that is the coordinate system x, y, z. Instead of origin, we take the dipole here minus q plus q, and the length of the dipole be 2l, and the position vector of q, let position vector of q, that is r dash vector, and here a point P where we have to calculate the potential due to the dipole, and that point P has the position vector, let r vector. Therefore, the potential at point P due to that dipole will be how much? Again we apply, join that line and apply the triangle of vector addition. The distance between these two will be how much? That is r vector minus r dash vector. So, here we calculate the potential at point P, potential at point P due to electric dipole, is given by, let potential V is equal to, the expression will be P dot R. So, P dot the distance, that is r minus r dash vector, divided by 4 pi epsilon naught into distance q, 4 pi epsilon naught cube of distance, that is r minus r dash vector magnitude whole cube. This is the potential at point P when the dipole is located arbitrarily. These two are the expressions related to calculation of potential due to that dipole. When the dipole is situated at origin, we derive the expression for potential, and potential in terms of gradient, and its special cases when that point lies the positive axial line, negative axial line, and also in that of equatorial line, and expression for potential when the dipole is located arbitrarily. Now, we have to calculate electric field due to the dipole from the expression of potential. So, calculation of electric field, electric field. Look here how we have to calculate electric field from the expression of potential. Let we consider that electric dipole that lies along the positive x axis with its midpoint at origin, and let the position vector be the r vector of that point P, which makes an angle theta with the electric dipole moment P. P is the electric dipole moment, where P vector is the electric dipole moment, and the direction of that of P from negative to positive. And let the point of observation P has the coordinate x, y, z. Now, we calculate the electric field intensity at point P. So, the electric field intensity, first the potential, the electric potential at point P due to electric dipole is given by, we have the expression V is equal to P dot R divided by 4 pi epsilon naught R Q, or we have V is equal to P R cos theta, theta with the angle between P and R, 4 pi epsilon naught R Q. Here R cos theta, look at that figure, as we take the coordinate of that point P be x, y, z, therefore cos theta will be how much? X divided by R, or x is equal to R cos theta from that line. So, in place of R cos theta we substitute x. V is equal to P x divided by 4 pi epsilon naught R Q. But we know, electric field is the negative gradient of potential. Electric field is the negative gradient of potential. Therefore, electric field E be the electric field intensity. Therefore, electric field intensity E at point P due to electric dipole. That E is equal to minus grad expression of potential, that is P x divided by 4 pi epsilon naught R Q. Here we have minus 1 by 4 pi epsilon naught P grad x by R Q. From the identity of gradient, if grad over phi psi be the two scalar function, then it will be phi grad psi plus psi grad phi. Here we can use that identity, minus 1 by 4 pi epsilon naught P 1 by R Q grad x plus x grad of 1 by R Q. Okay. just use that identity of vector. What is the value of grad x? Here grad x is equal to gradient I cap del by del x j cap del by del y plus k cap del by del z that operates over x. Therefore, we have grad x is equal to I cap del x by del x, all other terms are 0. So, I cap del x by del x exists. Therefore, grad x is equal to I cap. Here we just put, and again another property of gradient, grad of 1 divided by r to the power n is equal to negative of n r vector divided by r to the power n plus 2. That relation also can be used here. Here n is equal to 3. Instead of n we put 3. Using these two relations we can simplify the bracket term as minus 1 by 4 pi epsilon naught p, that will be I cap divided by r q, here minus 3 x r vector divided by r to the power 5. That is the expression for electric field E. Now, E is equal to minus p I cap divided by 4 pi epsilon naught r q plus 3x p r cap divided by 4 pi epsilon naught r to the power 5. Or E vector is equal to p I cap, that is p vector minus p vector divided by 4 pi epsilon naught r q plus 3 x p r vector divided by 4 pi epsilon naught r to the power 5. Here p I cap is equal to p vector, and again the value of p dot r, since we calculate p vector dot r vector, p vector is p I cap dot r vector, that is x I cap plus y j cap plus k z cap, that dot product result will be how much, that is p x, only x component exists. This is the value of p dot r. So, in place of p x we can substitute p dot r here, or E is equal to minus p vector divided by 4 pi epsilon naught r q plus 3 p dot r into r vector divided by 4 pi epsilon naught r to the power 5. From these two we get the term 1 by 4 pi epsilon naught r q as common. Inside that of bracket we get 3 p dot r into r vector divided by r square minus p vector. that is the required expression for electric field at point P due to that electric dipole. But when we calculate its magnitude will be 1 by 4 pi epsilon naught P divided by r cube 3 cos square theta plus 1 square root. Under simplification of that vector, we can find out that much. These are the expressions, that is the magnitude of electric field. This is the expression of electric field intensity at point P due to electric dipole. So, here we calculate the electric field from the expression of potential by using the relation electric field the negative of potential gradient and simplifying that equations, and finally we get that relation and its magnitude can be found out by solving that vector terms here. This is the magnitude. So, with the help of this video lecture we understand potential and electric field of a dipole. First, calculation of potential when the dipole is situated at origin. These are the expression of potentials, and then the special cases, and dipole located at arbitrarily, that is the expression, and the calculation of electric field from that of potential, the expression. So, with this useful and informative notes, let me wind up the session. Thank you.